Bismillahirrahmanirrahim. This video is about the inductor, how it works in a very simple way. Assuming a voltage source, AC voltage source, with a phasor value of 10 volts and 0 degrees. We'll assume for simplicity that it's positive here and negative here. And we'll assume that there is no other element in the circuit. It's a straight wire. Theoretically, the current should be infinity because the wire resistance is 0, but we'll assume again for simplicity that the wire's resistance is 1 ohm, so that the current in this circuit is 10 amperes. 10 and angle 0, the same phase like the voltage. Now let's assume that a resistance with 10 ohms has been added to the circuit. And as the name suggests, the resistance will resist the flow of electrons or the flow of electric current. It's like the electrons have to move through a pipe filled with rocks, meaning not all the electrons will pass to the other side. Applying Ohm's law, the new value of the current, now neglected completely the resistance of the wire, will be I equals 10 volts by 10 ohms equals 1 ampere. So 90% of the electrons passed through the wire in the first scenario have been blocked by the resistance. This is like the resistance is applying a force to prevent the electrons to move or to flow, and the voltage source need to perform work in order to push the electrons in the circuit and to push them against and despite the resisting force. And it's fair to say that the amount of work supplied by the source in order to overcome the resisting force is a sort of power or energy absorbed by the resistance. The amount of power absorbed by the resistance is defined by the formula PR, power absorbed by the resistance, equals the voltage drop across the resistance multiplied by the current through the resistance. Here in the circuit, the voltage drop across the resistance equals the voltage source value. It's 10 multiplied by 1 amperes, it's 10 watts. And again, this 10 watts represents the power or the work need to be performed by the voltage source in order to overcome the resistance force and in order for the current to continue to flow in the circuit. And now let's assume that this part of the straight wire has been reshaped in a form of electric coil, a number of turns. The flowing of electric current and AC electric current through the coil will generate a magnetic field around the coil. Each turn, let's assume that each turn produces a magnetic flux with the value phi. The total flux would be N multiplied by phi. N is the number of turns of the coil. This magnetic field is an energy because if you place iron filings around or near the coil, the magnetic field will attract the iron filings. This attraction is a force. And this energy is supplied by the source, by the voltage source. So like the resistance absorbed some power from the voltage source, the coil will absorb some energy or power from the voltage source, but it will handle it differently. It will store and release the power. The amount of energy stored on the coil in the form of magnetic energy or magnetic field, of course, will depend on the rate of change of the current generating it. Rate of change meaning the current must be changing first. A DC current passing through the coil would not cause any energy to be stored. The coil would act like a short circuit. But a changing current would cause the coil to store energy in the form of magnetic flux. The amount of magnetic flux stored or generated by the current would be is proportional to the rate of change of the AC current generating it. And it should follow the waveform of the current. If the current is a sine wave, the amount of or the magnitude of the magnetic flux generated would be a sine wave as well. Now, if we consider the first quarter of the current wave, the current value increases from 0 to maximum. The magnetic field or the magnetic flux generated on the coil would follow the same wave. It will increase from 0 to maximum. The coil is still an electric wire placed in a changing magnetic field. The presence of the coil in the changing magnetic field would generate, because of the magnetic field, an EMF on the terminals of the coil. And since in this quarter of the wave, in which the current value is increasing and the magnetic flux value is increasing, meaning more power is stored on the coil, which is supplied by the source. So the coil acts in a similar way to the resistance. The resistance, the voltage drop around the resistance would be like here is positive and negative. It's a voltage drop because the resistor absorbs power from the power source. The coil in this quarter of the wave absorbs or stores power which is supplied by the source. So the voltage drop or the EMF on the terminals of the coil will have a polarity similar to the voltage drop on the resistor, meaning this here is positive and here is negative. So when the current is increasing, when the rate of change of the current is positive, the coil acts similar to the resistor. It opposes the flow of the current. Or to be precise, it opposes the rate of change of the current. In the first quarter, the rate of change is positive, so the EMF generated on the terminals of the coil represents a voltage drop, opposes the increment of the current. So in the first quarter of the wave, when the current increases and the rate of change is positive, the voltage drop across the coil acts like an additional battery added to the circuit, that the positive terminal of it is connected to the positive terminal of the main voltage source. And hence the voltage drop across the coil opposes the main voltage source and hence opposes the flow of the current or the increment of the current. Applying Kirchhoff's voltage law to the circuit in the first quarter of the wave, the circuit has only one voltage rise, the voltage source value 10, which equal the two voltage drops in the circuit, IR plus the voltage drop around the or across the coil. In the second quarter of the wave, the current starts to decrease. This will cause the magnetic field on the coil to collapse, meaning that the energy stored on the coil would be released, and so there is no other path for this energy than the circuit. The energy stored on the coil would be released back into the circuit. This means that the coil is not acting anymore like a resistor, and the voltage drop across the coil is not anymore like a voltage drop. Instead, it will be acted like an additional battery added to the circuit, which negative terminal is connected to the positive terminal of the main voltage source. So the total voltage rise in the circuit is the sum of the voltage of the source and the voltage across the coil. Applying Kirchhoff's current law a second time would result 10 plus the voltage drop across the coil equal the voltage drop across the resistance IR, meaning that both the voltage source and the coil, or the energy stored on the coil, are now supplying to the resistor. We can see now that in the first quarter, when the current was increasing and the rate of change of the current was positive, the EMF generated across the terminals of the coil was like the resistance, a voltage drop opposing this increment in the current. In the second quarter of the wave, the voltage polarity reversed, so that the coil is releasing the stored energy on it back to the circuit, opposing the reduction in the current value. That's why the EMF generated on the coil is called back EMF. When the current increases and the rate of change of the current is positive, the coil stores energy, absorbs energy from the source and stores it, and hence the polarity of the back EMF is like the resistor. It's a voltage drop. When the current decreases, the back EMF, or the stored energy on the coil, will be released back into in the circuit, and the voltage drop across the coil would be like a voltage rise instead of voltage drop. In the frequency domain, the impedance of the coil is defined by the formula J omega L. Omega is the angular frequency, and the L is the inductance of the coil. It's a factor. It represents how much the coil can store energy for a certain amount of current. And as we said, when the coil stores energy, it represents some sort of resistance or impedance. So as well, and as per this formula, J omega L, the L defines as well the impedance or the resistance of the coil to the flowing of the current. The voltage drop across the coil, in terms of the impedance, is defined as J omega L I, this is in the frequency domain, equals ZL multiplied by R. ZL is the impedance of the coil. So in the frequency domain, it's J omega L. The power stored on the coil defined by the value Q to distinguish it from the real power P. It's a reactive power stored and released. And its notation is QL means the reactive power stored in the coil equals the voltage drop across the coil multiplied by the current flowing through the coil. And since the back EMF, or the voltage across the terminals of the coil, is generated mainly by the magnetic field, we can define it as well in the terms of the rate of change of the magnetic flux. Voltage drop across the coil equals minus N, the number of turns of the coil, multiplied by the rate of change of the magnetic flux on the coil, d phi by dt. The negative sign, again, because it's back EMF. It always opposes the change in the current value. The magnetic field is generated by the AC current. So we can define the voltage drop across the coil in terms of the rate of change of the current. It equals minus L di by dt. Again, L is the inductance. The L is proportional to the permeability of the core of the coil. The coil can be wounded around air, no material inside, or the core can be iron core to increase the permeability, or indeed it opposes the change of the current value. The permeability defines how easy the magnetic field can flow through the core of the coil. The inductance as well increases, or directly proportional to the number of the coil turns. Indeed, it's proportional to the square of the number of the turns of the coil. It's proportional to the cross area of the coil, and it is inversely proportional to the length of the coil, because increasing the length of the coil with the same number of turns means the distance between the turns increases, and this would affect the magnetic flux density. So L equals mu permeability multiplied by N square multiplied by the cross-sectional area of the coil divided by L. I'm sorry, this is small l. And the permeability equals mu naught, which is the permeability of free space, multiplied by the MR relative permeability, which is the permeability of the material of the core. If it's air, it will be only mu naught. If we use iron core, we will multiply this mu naught by a factor like of 1000. So it's much better to use iron core or core than other than the air. Although it's common to use the air core. Thank you very much for watching. I hope the video is useful and clarifies the topic a bit. Next video.